Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on February 5th, 2026, just 2 days ago. It introduces a speculative decoding framework that employs a lightweight block diffusion model for parallel drafting, achieving over 6 times lossless acceleration. The paper is titled DFlash, Block Diffusion for Flash Speculative Decoding. And as we'll see later, the resulting speedups compared to leading methods like Eagle 3 are really impressive. And for those interested in the implementation, the authors have shared their code on GitHub. On Hugging Face, the 4 billion, 8 billion, and 30 billion parameter DFlash weights are ready for download, with SG-Lang and transformers examples to help you get started. To visualize these gains, Figure 1 presents a direct speedup comparison on the QN38B model. The chart compares 3 setups across different tasks: the gray baseline, the green Eagle 3, and the blue DFlash. You can see that while Eagle 3 provides a solid 2 times boost, the blue bars for DFlash are consistently much taller. For instance, on the AIME25 benchmark, DFlash achieves a massive 6.08 times speedup. This confirms that the method scales exceptionally well, especially on reasoning-heavy tasks. To understand the mechanics behind these gains, Figure 3 breaks down the drafting latency in milliseconds. The gray bars show the baseline Eagle 3, where the time cost climbs steeply as we increase the number of draft tokens from 4 to 16, simply because it generates them one by one. In contrast, the colored bars for DFlash stay nearly flat across the board. This happens because the diffusion approach generates the whole block in parallel, so adding more tokens costs almost nothing in extra time. So, Figure 3 showed the speed. Now Figure 2 reveals the architecture that makes it possible. This diagram illustrates the DFlash inference design. On the left, we see the large target model processing the prompt. From this, DFlash extracts hidden context features, represented by the blue squares. These features are fused and injected directly into the key value cache of the draft layer, shown in the center green block. This injection is the secret sauce. It allows the small draft model to condition on the large model's deep reasoning, enabling it to accurately generate the output tokens on the right in parallel. While Figure 2 illustrated the inference flow, Figure 4 now details the training strategy. This diagram maps out the attention mechanism that allows the model to learn efficiently. On the left, the blue columns show the context features extracted from the target model, which provide the necessary grounding. On the right, the mask blocks grid reveals a diagonal pattern where yellow squares represent clean anchor tokens, and green squares are the masked tokens to be predicted. The extensive white areas are invisible regions, meaning attention is blocked there, so that each block learns independently without seeing future data. This clever masking enables the system to train on multiple blocks in parallel within a single pass. Alright, having seen the training setup in Figure 4, Table 1 now quantifies the actual performance gains across different tasks. Here, we see a head-to-head comparison on QN3 models, specifically testing math, code, and chat benchmarks. Focusing on the top section with greedy decoding, DFlash dominates. For example, on the GSM 8K math benchmark, it hits a 5.15 times speedup, whereas Eagle 3 hovers around 2 times. This advantage stems from the acceptance length, labeled here as tau. DFlash consistently gets 6 or 7 tokens accepted per step, which is double what the baseline achieves. So Table 1 covered the raw speedups. Now, Table 3 tests how DFlash holds up in a real serving environment, using SG-Lang. This table reports throughput and tokens per second across concurrency levels ranging from 1 to 32. Looking at the QN38B model on the Math 500 task, we see that DFlash starts with a massive 5.1 times speedup at low concurrency. Even when the load increases to 32 parallel requests, it maintains a strong 2.8 times advantage, delivering over 16,000 tokens per second. This consistency is driven by the high average acceptance length, or tau, which stays around 8 tokens regardless of the load. Wrapping up, 2 main takeaways stand out. DFlash effectively breaks the sequential bottleneck of inference by reframing diffusion models as parallel drafters, and it delivers over 6 times lossless acceleration on standard hardware. This approach suggests a scalable future, where diffusion and autoregressive models work in tandem for high-performance deployment. That's it for this episode of the AI Research Roundup. I'm Alex, thanks for listening.